finite impulse response filters. They are easy filters, non-recursive. By non-recursive, we don't expect any feedback. We don't expect any, let's say, delays on Y. So the outline of this lecture, we'll talk about the general information about FIR filters. FIR, if you remember, finite impulse response. And then we'll talk about convolution, something we've done in signals and systems. We've done it actually in 2 ways in signals and systems, or 3 ways. So there is the long way by using time reversal, sliding, then slide and overlap. And then we did the matrix method. And if I recall well, there was another method by using like shift and multiply. Okay, we'll talk about some implementations and linear time invariant systems. That's something we've done in signals and systems, so I'll go over it real quick. LTI, that's linear, that you can apply superposition. And time invariance, it's like if you have a delay at the input, you should have the same delay at the output. All right, but those are like very important properties in all signals. Let's say we may deal with in real life. All right, some general information about FIR filters. So a filter in general, you want to remove some unwanted components. Or filtering, you have, let's say, selectivity, you want to select some part of the components. So the finite impulse response, FIR, it's a class of filters that the output value is the sum of finite number of weighted values of the input sequence. So basically you have any certain sequence, you convolve it with the filter, and these filter coefficients will act like weights. You, let's say, multiply them with the signal coefficients to get the output. So the basic input-output structure of the FIR filter as a time domain computation based upon what's called a difference equation. Difference equation is basically h of n, that's the impulse response, and it is represented by the difference equation. So the unit impulse response of the filter is defined and shown to be completely described by filter via the convolution process. So this is some general information about FIR filters. Now, usually we want to deal with causal, non-causal signals. Basically, you have signals in the future, y of n plus 1 or x of n plus 1. So that's something not realizable. And that's why in math, when we deal with signals, we want to have them causal signal. So you only use present and past values. Non-causal filters, they use predicted values, let's say, not future values of the input. So this type of filter cannot be implemented in real-time applications due to the fact that the input is not yet available when the output has to be computed. So here is a typical example here of a non-causal system. You have x of n plus 1, x of n, that's the present value, and that's a delay, that's a past value. So here you have like a future value, like when you have like a future sample you're looking at. All right, so how to represent FIR filters? You can represent it by either looking at the coefficients like this, and it is assumed that the first coefficients you start at 0, or you can do it as summation of shifted deltas. So this one, h of n, equal, so the first one is shifted by 0 points, so that's a 2 delta of n. So that means that I have the weight 2 and there is no shift. Here the sign is -1, so minus, the value is 1 delta of, and here is the amount of shift 1, because the indices you start at 0, that's index number 1, index number 2, index number 3. Then you have the weight 3 delta of n minus 2, and the last coefficient is plus 0.5 delta of n minus 3. The order, as we mentioned before, it is the highest delay, so this one is third order. All right, so yeah, FIR filters could be given by showing the coefficients or something like this is the impulse response of this filter. So we have the filter with length 4 for coefficients, and the order is 3. And actually, the relationship between the order and the length, order equal length minus 1, equal the length minus 1. Now, the difference equation is basically the relationship between input and output. Now, for any general input sequence x of n, y of n equals x of n convolved with h of n. Now, h of n is given as this sequence of coefficients. So here, when we do a convolution with a delta, it's basically the output will be the same signal. And whenever we have a shift, the signal will be shifted by that value. So in this case, y of n equal x of n convolved with h of n. So the first convolution will be x of n convolved with 2 delta of n. So you'll get 2 x of n. Then we have minus x of n minus 1. Then we have plus 3 delta of n minus 2. So plus x convolved with delta x. We have 3 x of n minus 2 plus 0.5 x of n minus 3. So this is the simplest way to find like the convolution of input and output. And this is what is known as the difference equation. Difference equation. You don't have to worry about representing it in the summation form. It just simply you have x convolved with a set of pulses, and the output for each one of them is just a shifted version of x. If you remember, x of n convolved with delta of n minus k, the output will be x of n minus k. So the signal will be, let's say, remain itself, but it will be a shifted version from the original. All right, so unit impulse, probably we know that already. It has this property, delta of n minus infinity to infinity, that's equal to 1. That's one of the properties of the delta. Okay, so h of n basically is just shifted versions of pulses, and they are weighted by certain coefficients. And this is an example of this set of coefficients. So if you want to represent h of n, is that same example there. So it's going to be b naught delta of n plus b1 delta of n minus 1 plus b2 delta of n minus 2, and so on. Or basically summation of b of k delta of n minus k. And you have the values of k equal from 0 to infinity, or like the filter length. All right, so that's a typical example here. That's one of the representation, but usually in exam, I'll give you either this information, the coefficients themselves, or the impulse response. And from both cases, it is the same, let's say, representation. If I give you, let's say, for example, this impulse response, and I ask you what are the coefficients of this filter, is basically the constants multiplied with these deltas. So I have a length of 4. I have 4 coefficients. So the first one is 2. Here, there is no value, so that's a 1. So that's a negative 1. Don't forget the sign. And we have 3, and we have 0.5. All right, so that's the impulse sequence. The delay, we know that convolution with a unit impulse will cause a delay. So when you have n naught equals 1, so you have that what you call a unit delay. All right, so something already been seen before. So if you have a filter like this, b of k 0, 0, 1, so basically h of n equal delta of n minus 2, basically because I have my first index as 0, that's the second index at 1, third index at 2. So in this case, I have this filter So 0 times delta of n, it will cancel. 0 times delta of n minus 1, it will also cancel. Then I will have only delta of n minus 2. So when I do the convolution of this delta with a certain input sequence x of n, I will get x of n minus 2. So just show you that if you want to apply a delay to your signal, you just convolve it with delta. All right, so here is an example of delay. You start from 0, but when you apply the delay by 2 points, you start at 2. All right, so convolution, mathematically represented by this formula. Y of n equals summation from k equals 0 to m, h of k, x of n minus k, and we usually use the asterisk sign for convolution. So the output is basically the relationship between input and output is basically the convolution of input with a certain impulse response given to you. All right, so let's not worry about the math because we'll see that there are many ways to find the convolution instead of just applying that expression. So let's do, actually before doing the convolution, it's very important to know some information about how the output should look like. So usually when you have a signal x of n or a sequence x of n and you have another sequence, the impulse response h of n, this sequence has a length because we're talking about finite impulse response. So each sequence has a finite length. So let's say this one has a length Lx and this one has a length Lh. So the output sequence has a length of Lx plus Lh minus 1. And here is the relationship. That's actually length of Ln, of length of y of n. All right, so just some information that if your signal is limited from 0 to Lx minus 1 and the filter until m minus 1. So just some definitions, but when we talk into practice, you'll be given this information. So for example, here you have x of n. What is the length here? 1, 2, 3, 4, 5. So that's 5. And h of n, the length 1, 2, 3, 4. That is 4. So the output 5 plus 4 minus 1. That's going to be 8. So this is just like a hint or some information that will be beneficial for you before you start convolution. So like if you get the output sequence at a different length, that kind of like just a confirmation that you've done something wrong. You have to fix the answer. Now let's see what will be the answer if you convolve this sequence 2, 4, 6, 4, 2 with this sequence 3, negative 1, 2, 1. And I believe we've done something similar in signals and systems. So let me open the notes. I will do it the matrix way because the slides has the other way, like the multiply and add way. So the matrix way, basically, I have like something like this. So I have this is x and this is h. So x has values 2, 4, 6, 4, 2. And what is the value of h? 3, negative 1, 2, 1. 3, negative 1, 2, 1. And let's imagine this as a matrix. Okay. And you just multiply. Okay, hopefully nothing will happen. I don't know what this square is. All right, so 2 times 3, that is 6. You just multiply each element. So I have 12, 18, 12, and that's a 6, negative 2, negative 4, negative 6, negative 4, negative 2, 4, 8, 12, 8, yeah, 4, and then that's a 1, so it's going to be 2, 4, 6, 4, 2. And then we start summation, doing summation with diagonal. So the first element is this one, 6. Second element, the summation of these two. So 12 minus 2, that is 10. third element, 18 minus 4, that's 14, plus 4, that's 18. And okay, that's the third one. Fourth one. This one, you have to be careful with this. So 12 minus 6, that's 6, plus 4, 14, plus 2, that's 16. And then we have this one here. 6 minus 4, that's 2, plus 12, that's 14, plus 4, that is 18. And then we have minus 2 plus 8, that is 6, plus 6, that's 12. I'm going to continue here. 4 plus 4, that is 8. And then we have the last component, 2. So if you count the number of coefficients here, or the number of elements, so I have 1, 2, 3, 4, 5, 6, 7, 8. And that's kind of confirmed that we've done something, let's say, close to the right answer. And here are the values. So if you want to write the output, y of n, that's going to equal 6, 10, 18, 16, 18, 12, 8, and 2. And you have these 8 components here. The other way is been done in the slides. So you have your components, that's x of n, and you have h of n here. And you start the indexes at 0 and you finish at 7 because you assume the output has length of 8. So you start at this 0, you end at 7. Now for each row here, you shift the coefficients here, 3, 2, -1, 3, -1, 2, and 1, and then you multiply. So here you have a first, you multiply with original x of n. So you'll get 2 times 3, that is 6, 4 times -1, that is, 4 times 3, that's 12, 6 times 3. So the first row, you multiply everything by 3. So you get 2 times 3, that is 6, 4 times 3, that's 12, 6 times 3, 18, 4 times 3, that's 12, 2 times 3, that is 6. So that's the first row. Then the second row, you do a shift by 1 point. So here you do the shift and you start from here, and then you multiply all numbers by -1. So -2, -4, -6, -4, and -2. And then shift by 2 points, you multiply by 2. Shift by 3 points, you multiply by 1. And then you do the summation for all columns. And you should get the same exact answer. So 6, 10, 18, 16, 6, 10, 18, 16, 18, 12, 8, 2, 18, 12, 8, 2. So it is the same answer. So it is up to you to whether you do the matrix method or this method. Matrix method, I believe, is easier, but you have to be careful to do this, like when you do the drawing, draw well, have them aligned. Also, another thing, sometimes it happens, some students forget like some coefficients. And I remember an example I gave last year. When you have, for example, h of n equal delta of n plus 3 delta of n minus 2 plus 4 delta of n minus 3. And x of n equal delta of n plus 2 delta of n minus 1 plus 5 delta of n minus 2. So if you want to do the convolution, if you want to apply the matrix method, so what are the values of x and h? So here is x and here is h. So what are the values of x? I have 1, 2, 5. Now what about the values of h? So I have 1. Now there is no n minus 1. Notice here. So I'll put a 0. And 3 and 4. So make sure when you have, let's say you're missing a delay, the coefficient of that missed delay is 0. A lot of students forget this 0 and they will produce a wrong answer. So this signal, actually the length is 4, and this one the length is 3. the length of the output should be 6. 4 plus 3 minus 1. All right, so this one just a reminder that when you are missing a coefficient, put a 0 for that coefficient. So that's it about convolution. Pretty straightforward. In the exam, expect something like this. Convolution, there's a high chance that you'll have a question in convolution. You can, again, I'm flexible. You can either solve it this way or the matrix way I just did on the notes. All right, linear time invariant systems. So basically, we need to apply the two approaches, additivity and multiplicative properties. So linear time invariant systems is type of system that possess both linear property and the time invariance property. Linear property, we need to apply the superposition. So basically, I apply the inputs. Let's say the first input I apply, get certain output. Second input you apply, you get the output, and then you apply both inputs. You should get the same both outputs. All right. So the linear property means that the output is linearly related to the input. And time invariance means that the output for a particular input does not change depending on what the input was applied. So basically, whenever you have a delay at the input, you should get the same delay at the output. So it doesn't matter when you start your input, you should get the same output. And that's what it means here by linear time, time invariance. Now with linearity, like when you apply your input separately, you should get the outputs separately. Should not affect the output. All right. Basically here, cascaded means that you have things in series. Cascaded like this. So when you have one LTI system and another LTI system, or you can reverse their order, it's fine. You can start with the first LTI or finish with that LTI. Now the whole system could be combined of both LTI systems. So that's like the cascaded of LTI systems. And that's why actually it's preferable to have linear time invariant systems, because it doesn't matter where you start here or there, as long as they're in series, you'll get the same output. Okay. Now, how to visualize the time invariance? Basically, you apply first the input to the system and then apply delay to the system. You'll get a certain output. Or you can apply the delay to the input, apply to the system. If the system is time invariant, you should get both outputs the same. That's the time invariance property. So a discrete time system is said to be time invariant if when an input is delayed or shifted by a node, the output is delayed by the same amount. I believe there is an example here. Assume that you have the square law system or the square function where x of n equal x of n squared. Like that's the transformation here. Or basically you can model it like a black box. So here the input is x of n and the output y of n equals x squared of n. Now determine if the system is time invariant or not. So basically the first part, apply the delay. So you have x of n minus n naught. So here x of n minus n naught applied to the system. Now notice here the square happens only to x and not, there will be no effect. So you'll get x of n minus n naught squared. Now the other part says that, okay, so apply x of n to the system. That's the delay, TS. No, sorry, that's the system. And you'll get x squared of n. Then apply the delay, T by n naught, not TS, by n naught. So you'll get x squared by n minus n naught. Because this is the change in the amplitude, it should not affect the time shift. Here, actually, if I want to model it proper, in a, let's say, more proper way, you have x of n. You apply the delay by n naught, you'll get x of n minus n naught, and then you feed it here, and you'll get that output. Since they are the same, then the system is time invariant. So second, we take x of n as the input to the squared system, and then you apply the delay. So since two outputs are the same, then the LTI system here is time invariant. Or you can refer back to the notes in signals and systems. I think we've done plenty of examples there. All right, so time flipping or time reversal. So x of n, and you have your system, and the output, oops. Okay. And the output here should be x of negative n. Now first, let's try doing shift, then reversal. So I have x of n. Now we'll do delay unit by n naught. So I have x of n minus n naught. And then we apply time reversal to the system. So that's the system. The output will be x of negative n minus n naught. Notice we only reverse negative n, not the whole thing. Okay. So that's the one here, x of n. Then I did the delay, x of n minus n naught. The reversal, x of negative n naught. So that's the output here. Now let's try the opposite, or like flip between the order between the system and the delay. So I have x of n, and then apply it to the system. So I have the system here. I will get I'll get x of n minus n naught. Oh, this is the system, x of negative n. Then apply the delay by n naught. So it's going to be x of negative. Now I'll do the shift to n naught. And that's going to be equal to x of negative n plus n naught. And you can tell they are not the same. So in this case, the time reversal system is time variant, or is not a time invariant system. So since the two outputs are not the same, the time flip or time reversal system is not time invariant, or you can say time variant. It is a time variant system. Right? Is it clear how to test time or time invariance? So you have the system and the delay. So first thing, you do the delay, apply to the system, see the output. The second part, apply the system, do the delay, and check the output. If they are the same, then the system is time invariant. If they are not the same, then the system is not time invariant. So that's about time invariance. Linearity is something basic. So basically you have an input x1. You give it a certain weight a1, and you'll get a certain output y1. Oh, sorry, apply it to a certain system. Oh, no, before applying to the system, you have another input x2. You have another coefficient a2. You add them both together, and then you apply it to the system. So that's an adder. And you will get y1 plus y2. Or you get a y, let's say. Or you can do like this. x1, apply it to the system, scale it by a1, and you have x2 applied to the system. You will get multiplied by a2, add them, and you get a certain output here. Just check these two outputs. So that's it. It's just where you apply the system here. So here you have x1, you apply to the system, you're getting y1. You scale it by a constant, and you'll get certain output here. Same thing for another input, apply it to the system, you get y1, scale it, add them, you'll get a certain function. Let's call it up y or w of n. The other part, you have x, you scale, another x, you scale, add them, then apply it to the system. And again, compare both outputs. So let's try the same concept for the square function. So let me open the notes and assume that the function x of n, my system here is the square, and my output x of n squared. So it's better when it comes to these problems, draw the diagram. So you have x1 of n, apply it to the system, squared, you will get x of x1 squared of n, and let's call this one y1. Then you scale it by a1. So you have a1 y1. Keep it here. Same thing. I'm going to do another stream, x of n, apply to the system, squared. So I'll get y2 equals x2 of n squared. Scale it by a2, and you will get a2 y2. Add them together, and you will get a1 y1 plus a2 y2. Or you can substitute a1 x1 squared of n plus a2 x2 squared of n. So that's the first part. The other part, we'll do the multiplication by constants, we'll do the addition, add them, then apply it to the system. So here you have x1 of n, multiply it by a1, you'll get a1 x of n, x1 of n. Second, x2 of n, you multiply it by constant a2, you get a2 x2 of n. Then you add them, so you have a1 x1 of n plus a2 x2 of n. Then we apply it to the system, square. What we will get here, you will get a1 k squared x1 of n squared plus a2 squared x2 of n squared plus, I believe it's going to be 2a1 a2 x1 x2. x1 of n, x2 of n. And you can clearly say that this coefficient causes an issue, and also we have the squares here, so they are not the same. So you can say 1 does not equal 2. So in this case, the system is not linear. I think it's already been solved in the slides. Sometimes in two properties, additive scaling, done that. Yeah, that's a typical example here. Current slide. All right, so that's the first part. You do the transformation, then you do the scaling. That's the other one here. So you have alpha squared to alpha. They are using alpha and beta, but it's a1 and a2. So you have this coefficient or this term that does not appear there. Also, you have beta and alpha. We have alpha square, beta square. So since they are not equal, we can say that the square law is not a linear system. Okay, some properties about convolution. I think we've already that. So commutative property, you can swap. So x convolves h equals h convolves x. The convolution with delta will cause a shifted version of the signal. Associative property, pretty much like the multiplication. If you convolve x1 and x2 alone, then you convolve the result with x3. You can do it convolve x2 and x3 alone, then you convolve the result with x1. So that's what you call associative property. Distributive property, you have x1 plus x2 convolved with h of n. So you take h of n, convolve it individually with x1 and x2, and add their results. Convolution again is pretty much like multiplication. And that's it for this part of the lecture. As I mentioned, since we are lecture behind, I'll keep the worksheets for you. You can work on them on your own. I already uploaded them onto Moodle. So actually there are two worksheets for this lecture. Let's go over them real quick. So that's the first worksheet here, or this is the lecture. Now I open the lecture one more time. So that's the first tutorial. So let's see here. So a linear time invariant system is given by the following expression. Yeah, let's say when you are given an expression like this, can you determine what is the impulse response? How? Okay, remember, what is the impulse response? Yeah, okay, when you are given like this, you have y of n equal to x of n plus 4 of x n minus 1, 2x of n minus 2. And I ask you, what is the impulse response of this function? Now remember, what is the definition of impulse response? It's the output of the system when the input is delta. When the input is delta. Now, if you look here, change the input into delta. What is your input in the signal? X of n. So instead of each x, put delta. So here it's going to become h of n equal 2 delta of n plus 4 delta of n minus 1 plus 2 delta of n minus 2. This is how you determine the impulse response easily. So that's it. Once you have all elements, you have the delta, and you can basically do everything. So compute the values of y of n over the range of 0 to 10 when the input of the system is given by the following functions. So for each one of them, you do just shifting. So this one actually is recommended to do it graphically. Plot the stem graph of x of n. So you draw this one. And determine the response of the system to unit impulse input according to the plot. So basically you can draw this one. Actually, this is not a finite signal because it's going to be one with, let's say, when time goes larger than 5. Okay, let's say this one here, an LTI system is given by the following. Find the impulse response, again, x delta of n, 2 delta of n minus 1, plus 3 delta of n minus 2, 4 delta of n minus 3, 2 delta. Order is 5, I believe, or 4. Order is 4. The length is 5. Solve the output of the system if the input is given by the following function. By the way, those are supposed to be deltas. Let's just have typos here. So this is delta of n minus 1, delta of n minus 2. So you have the coefficients here. You have 1, negative 2, 3, negative 4, 2. You have the coefficients here, 1, negative 1, 1. You do the convolution the way we did it, like the matrix way or like that definition. Anyways, the solution is provided here. So tutorial 4, I believe, solution. Yeah, there we go. The solution is there. Second part, this one is not doing the matrix form, but you can apply the matrix form and you will get the same exact answer. Sketching should not be an issue, I believe. Drawing the pulses. So at 0 it's 1, at 1 it's negative 3, at 2 is 6, and so on. Okay, that's the first worksheet. I believe the second one will be related to convolution. Sampling. La, I don't think so. No. I've not write the quiz. Once I write the quiz, I'll confirm with you. Okay, so the other part, tutorial 4, part 2, this one. LTI system described by the following differential equation. Determine the FIR filter coefficient of this LTI system. Yeah, if you have something like this, and I ask you what are the coefficients? Yeah. Okay, so apply the summation. So, and you'll find that y of n equal 0 plus x of n minus 1 plus 2x of n minus 2 plus 3. Just a substitute like summation. Then you take the coefficients. So it's going to be 0, 1, 2, 3, 4, 5. And from looking here, actually 0 to 5. So it's from 0 to 5. Find the impulse response h of n. We found it. And draw the stem plot of the range from -2 to 5. Anyways, work it out. That's something we did last week. You have the find the gain at different frequencies. Frequency response given the following function, determine the difference equation. So basically that's like frequency domain. You can send it back to a Z transform to h of z, and you do the inverse. It's going to be shifted versions of deltas. And so on. Anyways, give it a try and let me know if you need any help. Okay. What is the material for the quiz? Okay. Okay. So let me stop the recording for this one so we can start another lecture. Okay, هيك خلصنا ال FIR.